We use them every single day, right? The computers in our pockets, on our desks, they honestly feel like magic a lot of the time. Well, today, we're going to pull back that curtain. We're going to see how they actually turn a simple click into a complex command. Let's get into it.
I mean, think about it. It all starts with such a simple action. A click, a tap, a single key press. But that one tiny input kicks off this incredible chain reaction inside the machine. So we're going to follow that chain, from your finger all the way to the final result you see on the screen.
All right, so before we get into any of the hardware, the nuts and bolts, we need to understand a computer's most fundamental job. It's not about the flashing lights or the fancy screens. At its absolute core, a computer really only does one thing. It turns raw, messy data into useful information.
So what's the difference, really? Well, data is just stuff. It's a jumble of raw, unorganized facts. Numbers, words, pixels, all without any real context. It doesn't mean much by itself. Information, though, that's what you get when all that data gets processed and organized. Suddenly, it has meaning. It actually helps you make decisions.
Here's a perfect way to think about it. Imagine a store manager. They've got a long list of item codes and how many of each they have. That's the input, just raw data. The computer then processes it. Maybe it compares those quantities to a minimum stock level. And the output? A super clear, useful report that says, hey, you're running low on these shoes. That's information. It's the journey from chaos to clarity.
Okay, so how does the machine actually pull off this transformation? Well, it turns out that every single computer, I don't care how big or small it is, accomplishes this with 4 basic jobs. This whole thing is called the information processing cycle.
First up, it takes in data through an input device, like your keyboard or mouse. Second, it processes that data, doing all the heavy lifting, the calculating, the organizing. Third, it has to keep track of everything, so it uses storage. And finally, it produces the result as output on something like your screen or a printer. Input, process, storage, output. It's that simple, that powerful, and it's universal.
And this 4-step cycle applies to absolutely everything, from the microcomputer on your desk, which is what most of us use every day, to the mini computers that run things like an ATM. Then you scale way up, and you've got these massive mainframes that banks use to handle millions of transactions. And at the very top of the mountain, you have incredible supercomputers predicting the weather. They all follow the exact same principle, just at a wildly different scale.
We've covered the what, so now let's dive into the how. We're going to go inside the machine, zoom right in to find the components that do the actual work, the real thinking, the digital brain.
So let's meet the star of the show, the Central Processing Unit, or CPU. If a computer were a person, the CPU is its brain, no question. This tiny little chip of silicon is where everything happens. It interprets and carries out every single instruction, making it the engine where all that processing we talked about actually gets done.
But this brain, it has 2 key parts that work together. First, you've got the arithmetic logic unit, or ALU. You can just think of this as a super fast built-in calculator. It handles all the math and all the logical comparisons, like, is this number bigger than that one? And second, you have the control unit. Now this is the boss. It doesn't do the calculations itself, but it directs the whole operation, telling the ALU, the memory, and everything else what to do and when to do it.
Now, the CPU is incredibly fast, but it's useless without data to work on. And that data lives in what we call a hierarchy of memory, which is really just organized by speed. At the very bottom, you've got your long-term storage, your hard disk, or your solid-state drive. This is like a massive filing cabinet where everything lives permanently. It holds the most stuff, but it's also the slowest to get things from.
Having to go to that big filing cabinet every single time would be way too slow for our speedy CPU. So instead, the computer pulls what it needs for the current task into RAM, or random access memory. Think of this like the computer's temporary desk or workspace. It's way, way faster than the hard drive, but it's also volatile, which is just a fancy way of saying when you turn the power off, everything on this desk gets wiped clean.
But believe it or not, even RAM isn't quite fast enough for the lightning-quick CPU. So that's why there's an even smaller, even faster layer of memory called cache. The computer is smart enough to place the data you use most often right here so the CPU can grab what it needs instantly without having to make that quote-unquote long trip all the way to RAM.
And at the very, very top of the pyramid are the registers. Now, these are tiny, tiny amounts of memory located directly inside the CPU itself. They hold the exact piece of data that the CPU is working on in that precise instant. This is the absolute fastest access you can possibly get. Okay, so we have the brain and we have the memory, but they're all just electronic circuits, right? They're just physical things. how do they actually represent a number or a letter or a photo? How does a physical object hold on to an abstract idea? The answer to that huge question is actually incredibly simple. It's the bit. Everything, and I really mean everything in a computer, boils down to this one idea. A bit is just a switch. It's either off, which we represent with a 0, or it's on, which we represent with a 1. That's it. And by stringing together billions of these tiny on-off switches, a computer can represent any piece of information you can possibly imagine. Okay, so we've basically built a single working computer from the ground up. But the true power of modern computing, the thing that changed the world, is when we connect them all together. So it's time to zoom back out and see how these digital brains talk to each other. The first step is what's called the local area network, or a LAN. This is probably what you have in your home or your office. It's your Wi-Fi network. It's a network that just connects a group of devices in a small area, letting them share files, printers, and usually a single connection to the outside world. So what happens when you start connecting those individual LANs together? Well, then you get a wide area network, or a WAN. A WAN can stretch across a city, a country, or even the entire globe, just by linking all these different local networks together. This is how a company's office in New York can talk to its office in Tokyo.
And that brings us to the ultimate WAN. The internet itself. It's really nothing more than a giant global network of networks. It's just a massive, sprawling collection of interconnected LANs and WANs, all agreeing to speak the same digital language, which allows data to flow from pretty much any computer to any other computer on the entire planet.
So, there you have it. We've journeyed from a single mouse click all the way to the global internet. From raw, messy data to truly useful information. And from a simple on-off switch to a planet-spanning network of supercomputers. The basic ideas are surprisingly straightforward, but what they create has completely changed our world. Which really just leaves one question, doesn't it? What's next?